This is part of a worksheet that we would have done on the last day of class. There are some other non-fluid stuff on it, but I'm just going to have you do the fluids problems that are on this worksheet. Okay, so first problem, when you ascend or descend a great deal when driving in a car, your ears pop, which means the pressure behind your eardrum is equalized to that of the outside. If this did not happen, what would be the approximate force on an eardrum of area 0.2 square centimeters if a change in altitude of 1,250 meters takes place? So in order to figure out what this force is, what we're going to think of is, imagine your eardrum is like, as if it's a circular disc membrane, right? And we've got, if it stays rigid, if it doesn't deform too much, of course, the deforming is what causes it to pain to happen in your ear when you go down, further on down in elevation. But let's suppose it doesn't deform much, and so it keeps it the same area, and there's some internal strain inside your eardrum that keeps the pressures unequalized. In other words, we have the pressure outside times the area of the eardrum is equal to the force being applied from the outside. We got the pressure on the inside times the area of the eardrum is equal to the force going in the other direction from the inside of your ear. And then, of course, we've also got some sort of force being pushed back by your eardrum. So let's just talk about the difference between the forces due to the air pressure on the inside and the outside. And the idea, so the idea is the net force due to those that's not really the net force on your eardrum. Of course, your eardrum isn't going anywhere. There's a third force, which is sort of the sides of your eardrum holding it in place, and that's what causes the pain. But this is just the net force caused by the air pressure difference is equal to the outer pressure times the area times the inner pressure times the area. That's the difference in pressure times area, or difference in forces. How are we going to get that difference in, we're given the area of the eardrum here, how are we going to get the difference in pressures? Well, we can use rho GH to get the difference in pressure if you go down by a certain distance in the atmosphere. Now, we have to be a little bit careful here, because I said earlier on in the videos that you can't use rho GH unless rho is constant, and in the atmosphere the density of air isn't constant, but in this case it is over a distance of 1,250 meters. The density of air doesn't change that much. It changes a lot if you go up much higher out, towards the top of the atmosphere. The pressure would, the density would get a lot different up there. But over this elevation change, the density of air is approximately constant. And so the difference in pressures is rho GH. So that tells us what the difference in pressures is, and rho GH times the given eardrum area expressed in square meters gives the force, the difference in the forces due to air pressure on the two sides. Of course, again, there's a third force, which is around the edge of your eardrum. The whatever the structure is of your inner ear, the cartilage is pulling on the eardrum, and that's causing pain in your eardrum. So the sum of those three forces are in fact equal to 0, but this is just the two air pressure forces. 2. Simple model considers a continent as a block, like you can think of it as a cubic block in this case. We're given the density of the block. It's floating on the mantle rock around it, which has a higher density in this case, so it's floating on a fluid of higher density, and therefore it doesn't sink, it's only partially submerged. Assuming the continent is 35 kilometers thick, so this dimension is 35,000 meters, estimate the height of the continent above the surrounding mantle rock. So this sounds like that ice cube problem. In this case, it looks like I did something maybe a little bit different than the ice cube problem. I called X the height of the continent that is underneath the liquid mantle rock that it's floating in. So when if we calculate x in this problem, that's not the answer. We want to know this distance. This distance will be 35,000 meters minus x. Okay, so let's first find x. That was the way I'm approaching it in this solution. And the idea is, well, we're going to balance forces here. What forces are summing to cause this thing to neither accelerate up or down? Well, it's got a certain weight going down of that continent, right? Just mg. And it's got a buoyant force going up, and they're balanced, as shown in the picture here. So let's first calculate the mass of the continent. The mass of the continent is the density of the continent material times the volume of the continent. Now, we're not told the cross-sectional in the horizontal sense, cross-sectional area of it. So I'm not going to let that worry me too much. I know the height of it. I know this dimension. I don't know what area it has if you look down at the top. We're just going to call that unknown area A, and we'll find out it cancels out down below. So don't worry about that too much. So that's the mass of the continent. Therefore, the weight of the continent is that number times A times little g, right? So that's one of the forces going down. Now, the other thing that's going to be balanced with is the buoyant force, right? The buoyant force is equal to the weight of the mantle fluid which is displaced. And that is equal to the density of the mantle fluid times the volume of the mantle fluid displaced. Well, the volume of the mantle fluid displaced is the cross-sectional area A times x, right? Whatever volume is sitting underneath the fluid. So A times x is the volume of the mantle fluid displaced. That times density gives mass of the fluid displaced, times little g gives weight of the fluid displaced. So I'm just going to set those two things equal to each other because those two forces have to balance out if it's not accelerating. When we do that, the little g's cancel and the a's cancel. That's kind of nice. And that allows me to solve for x in this case. I've expressed it in kilometers here, but we're not asked for x. We're asked for how high this thing floats above. So that number is 35 kilometers minus x, 5.3 kilometers. 3. A beaker of water rests on an electronic balance that reads 975 grams. A 2.6 centimeter diameter solid copper ball attached to a string is submerged in the water. Okay, so it sounds like the water by itself, including the beaker that it's in, has a mass of 975 grams. I just write that as 0.975 kilograms. After that, a 2.6 centimeter diameter solid copper ball attached to a string is submerged in the water. It's a ball. You got to know the formula for the volume of a ball of radius r, and in this case that's 4/3 pi r cubed. That's something I definitely would have given you on this worksheet, and usually if I forget, people ask me, but it's not something I expect that everyone knows. Formula for the volume of a ball of radius r. All right, so this copper ball is submerged, and it does not touch the bottom, so it's just sitting in the fluid with the string still on the top. What is the tension in the string, and what is the new balance reading? So to get the tension in the string, what I can do is think of a free body diagram for just the copper ball. Here it is right here. It's got some new tension going up after it's been submerged, in addition to the buoyant force, and then a weight force going down. So to calculate the weight force, I need to multiply the density of copper, which you got to look up in a table of densities, that's from the book, times the volume of copper, the volume of the copper ball, and that's 4/3 pi r cubed. So this is the diameter of the ball divided by 2. That's the radius cubed. That would be the mass of the copper times little g gives me the weight of the copper. So that's whatever that number is, 0.8027 newtons. That's this force going down. The tension is what we want to know going up. And then the buoyant force we can also calculate. The buoyant force is equal to the weight of the water displaced. So that's equal to 4/3 pi r cubed, the volume of the water displaced, times the density of the water, which is 1,000. That gives me the mass of the water displaced, times little g to get the weight of the water displaced. That's 0.09019 newtons. Okay, so this plus this minus this equals 0, and therefore I can solve for the tension in the string, 0.712 newtons. Also, what's the new balance reading? For the new balance reading, we could, let's see. It looks like there are several ways you could choose a free body diagram for different kinds of objects. I chose my object to be just the beaker plus the water, not including the copper sphere, and said what forces are acting on the beaker plus the water. Well, the scale's underneath it, so it's pushing up on it, and that's what we want to know. How hard is the scale pushing up on it? That's what the scale is supposed to be calibrated to read. Now, the buoyant force is pushing up on the copper ball, so that means the copper ball is pushing down on the beaker plus water with the buoyant force, and we calculated what the buoyant force was, so we already know what that is. And we also know the weight of the beaker plus the water. We're told its mass is 0.975 kilograms, so multiply by little g, that gives the weight. The sum of these three y components equals 0. And we can use that to solve for the scale reading. The scale reading is 9.645 newtons if it read in newtons. Now it actually reads in grams, so we've got to say, well, let's see. This force that we've computed here is equal to some unknown m times little g, and therefore the unknown m is that force divided by little g. That I've gotten it here in kilograms. This scale reads in grams, so I've got to convert that new kilogram reading to a gram reading, 984 grams. So it's changed a little bit. It reads a larger mass reading after you've submerged the copper ball. Finally, problem 4, we're not going to do 5 and below. Problem 4, we have a copper weight placed on top of a 0.4 kilogram block of wood. We're given the density of the wood. It's floating in water. What is the mass of the copper if the top of the wood block is exactly at the water's surface? So somehow, by some miracle, the wood is floating just with its surface below the water, and the copper's bottom is just above the water. They meet right at the surface of the water. Well, in this case, again, we don't really. I guess there might be several ways to think about what free body diagram to draw, but I chose the wood itself without the copper to be the subject of my free body diagram. And so in this case, what are the forces that are acting on the wood? Well, it's got its own weight going down. Let's see. We're told the mass of the wood is 0.4 kilograms, so we know its weight is mg. In addition, the copper is pushing down with its weight on top of the wood. In other words, the wood has to counteract the copper's weight, and therefore the copper is pushing down on the wood with the copper weight. So we need to figure out what the mass of the copper is and multiply by little g there. And that is our unknown, right? We want to know the mass of the copper, so that's our variable, m, the mass of the copper times little g. And then finally, there's a buoyant force going up on the piece of wood, right? Buoyant force from the fluid, and that's the volume of the wood times the density, so that would be the volume of the fluid displaced, times the density of the fluid times little g. Okay? Now, we're given the mass of the wood, and we're given the density of the wood, so mass equals density times volume. We know the mass, we know the density. We can solve for the volume of the wood. That's what I've done over here. And I can substitute that into this up here to figure out what the buoyant force is. That's this expression here. And then the sum of those three force y components is equal to 0. the buoyant force minus the copper weight minus the wood's weight. I'm sorry, I said those wrong backwards, but sum of those three is equal to 0, and that allows us to solve for the unknown mass of the copper that's sitting on top.